Okay, in this video we're going to talk about permutations. Permutation is the act of arranging members of a set. So, permutation is an act of arranging. Or, if the set is already arranged, so it is also an act of rearranging members of a set into a sequence or order. So that process is called permuting. Unlike combination, combination is a selection of some members of set regardless of order. Here, in permuting or permutation, order is important. Okay, remember that in permutation, order is important. Okay, let us say, for example, the very famous combination lock set that we are seeing in the market. Okay, it goes something like this. There's some numbers here. Mostly there are three possible combinations for the number, and this number here is from 0 to 9. In here there is 0 to 9, and in here there is also 0 to 9 numbers to choose from. Okay, so in this case, this is widely called combination lock set, but in reality this must be called permutation lock. You know why? Because if the combination of this is example 4, 7, 2, the order is important in this case. This lock won't unlock not if you don't put here on the first place 4, 7, and 2 on the third place. In short, it must be exactly 4, 7, 2 in that same order. 2, 7, 4 will not do it, nor 7, 4, 2. So, I would like to emphasize that in permutation, order is important. Permutation is called unordered combination. Some mathematician called permutation as unordered combination. Now, if this bothers you, for an easier recall, when we talk about permutation, then we talk about position. Okay, position is important. The number of permutation of n distinct object is denoted by n factorial. So n factorial. This is a symbol for factorial, which means the product of all positive integers less than or equal to n. But take note, 0 factorial is equal to 1. You must take note of this convention. This is globally accepted convention. So, before we go further into permutation, let us understand and have some examples of factorials. Let's say, for example, we are asked to find 4 factorials. Remember, factorials is defined as the product of all positive whole number integers less than or equal to n. So this is simply equal to 4 times 3 times 2 times 1. And if you multiply this, you will get a product of 12 times 2 times 1 is equal to 24. So 4 factorial is equal to 24. Let's have another example. For more clarity, if we have 10 factorial, all we have to do is to multiply all the whole number from n up to 1. Therefore, it's just simply the product of all positive integers less than or equal to n. This will be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 then times 1. So therefore, if you multiply this and you get the product, that will be the result of 10 factorial, or that is simply equal to 3,628,800. If we want to get the value of 2 factorial, 2 factorial is equal to 2 times 1, then we will have 2. Remember, 0 factorial is equal to 1. There are two types of permutation. The first one is when repetition is allowed, and the second one is when repetition is not allowed. Let us take, for example, the previous example from the permutation lock, or the widely known as combination lock. In that case, we can have a combination of 3, 3, 3. Or otherwise, we can also have a combination of 0, 0, 3. Or we can also have 1, 0, 1. Obviously, in this case, repetition is allowed. Let us try to deal with it one by one. So, when repetition is allowed, when a thing has n different types, for example, in lock set, we have n different types, and we have n choices each time, then that is a permutation with repetition allowed. We have n different types for the first slot, and for the second slot, we also have n different types, and on the third slot, we have n different types. Correspondingly, we have n different choices for the first, second, and third. So therefore, we have n different types, and we have n different choices each time. In this case, this is a type of permutation where repetition is allowed. If we are going to choose R of something that has n different types, then the permutation will be n times n times n all the way times the R number of times. You have to multiply that by n R number of times. Let us take, for example, the permutation lock that was given earlier. We have 3R of something that we have to choose from 10 different types, from 0 to 9. So here we have 10 choices, and another 10 choices, and another 10 choices for the third slot. Every time we have n different choices. So in short, we have to multiply 10 times 10 times 10. This is equal to 1,000 possibilities. And if you try to simplify 1,000, this is equal to 10 cubed. Now notice here that we can derive a formula from here. If 10 is n and r is the number of times that you are going to choose from something, then therefore we can say that the permutation of choosing r of something that has n different types is n raised to r. Now let us talk about permutation without repetition. For example, we have a rack of or a set of pool balls. These are the 15 balls, and this is the mother ball or the white ball. So all in all, it is 16 balls. Remember, in permutation with repetition, our choices reduce every time. So, in other words, our choices gets limited each time. So let us take, for example, in how many ways could 16 pool balls be arranged in a rack? Let us have this example. Let us try to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. For example, this is a rack of 16, and this is the balls that we are going to choose from, including the mother ball or the white ball. So in the first choice that we are making, we have 16 possibilities, 1 to 15 plus the mother ball. Now, for example, if we had chosen number 2 here, we cannot choose it again here because it's already taken the place of the first slot. It means on our second slot, we will only have 15 available possibilities because one ball has already taken the place of the first slot. And on our third slot, we will be having 14 possibilities because 2 balls already taken the first 2 slots, and so forth and so on. On the fourth slot, we have 13, we have 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So for the 16 balls, all we have to do to get the number of permutation, we have to multiply all these possibilities in the slot. This is applying the slot method. I call it as slot method. But try to notice here. If you try to notice, this is 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, it is simply the product of all positive integers less than or equal to 16. And somehow, that is similar to factorial, right? So instead of writing the long method, which is the slot method, we can say that the permutation of arranging 16 pool balls on a rack is simply equal to 16 factorial, and you will have the same answer. And 16 factorial is somewhat equal to, and it is equal to something like 20 trillion if I read it correctly. Now, suppose we do not want to choose all of them and arrange them in a rack. Suppose that we only want to choose 3 out of the 16 pool balls that was held as an example lately. Now, what are we going to do now? So, we will be having 3 slots, okay, using the slot method. In the first place, we have 16 possibilities. That is correct, including the mother ball, which is the white ball. From 1 to 15 plus the mother ball, you will have 16 possibilities in the first place. On the second place, because you have chosen 1 ball on the first place, we only have 15 possibilities on the second place. And on the third place, because 2 balls have already occupied the first 2 slots, we only have 14 possibilities. So, the number of permutations of picking out 3 balls from the set of 16 pool balls is equal to 16 times 15 times 14. And that is actually equal to somewhat 3,360 permutations. But this is using the old method or the slot method. Now, you may wonder if the factorial notation is applicable in this case. Because when you try to write 16 factorial, what will it do is it will multiply all the positive integers from 16 all the way to 1. But we do not want the 16, all the 16 balls. We only want 3 of them. So what are we going to do to apply the factorial notation? Well, there is a neat trick with that, okay? So, notice that we do not need, if we have this 16 factorial, okay, and 16 factorial is equal to 16 times 15 times 13 times 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that is 16 factorial. There is 14 here. Okay. So therefore, actually, we do not need this one. We only need 3 slots. As in the previous example, we only need 16, 15, and 14. How are we going to do this in factorial notation? Okay, if we are going to, if we have n number of things, n number of things, and we are going to take 3 r of the time, or r things from them. So this is the notation for permutation. Sometimes you will see P and R. You have n number of things taken r at a time. So if we have here on the numerator n factorial, on the denominator we simply subtract the number of choices that we have, and it will cancel out on the numerator. What I mean to say is, if we have n factorial on top, on the denominator, all we have to do is to have n minus r times the quantity factorial. So this is the general formula for permutation. Okay. In other words, if we have 16 factorials, which is written as 16, 15, 14, 13, then we have here 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And we have 16 minus 3, and that is quantity factorial. This is actually 13 factorials. Is that correct? So if we will have 13 factorials, that is actually 13 times 12 times 11 times 10, and so forth and so on until it reaches 1. Try to notice here, up and below, all the factors will only be cancelled out up to 1. And what remains is 16 times 15 times 14, exactly the same as the slot method. So to make a conclusion in permutation without repetition, if we have n number of things taken r times, and then the formula is simply n factorial over the quantity n minus r factorial, wherein r is the number of choices we are going to make from n different things, and different things taken r at a time. Example: in how many ways can first and second place be awarded to 10 people? Before solving or jumping into a problem, you first have to analyze it yourself. Is order important? If order is important, then you are looking at a permutation. If order is not important, then it is a combination. Now in this case, we have 10 people or 10 persons, and we are going to choose first and second place. If we award, for example, you have 2 slots here, if we award the first place here, and first place can never be second place, therefore order is important. So what are we going to do? In the slot method, what happens is, here we will have 10 possibilities, and on the second slot we will only have 9 possibilities. leaving us with 90 permutations. If we try to apply the formula that we have just derived, n PR is equal to n factorial over n minus r quantity factorial, wherein n factorial is equal to n number of people, which is 10 factorial over 10 minus how many choices did we make? 2 quantity factorial. That is equal to 10 factorial over 8 factorial. Now, one way of solving this one is to write 10 factorials here as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then divide that by 8 factorials, which is 8 times 7 times 6 times 5, 4, 3, 2, and 1. Notice here that from 8 onwards, the factors will just cancel out, leaving us with 10 times 9, which is equal to 90. And 90 here is equal to 90 with the slot method. Let us now jump into different types of permutation problems. Consider arranging 3 letters. For example, we have letters A, B, and C. How many ways can this be done? How many ways can we arrange letters from A, B, and C? The possible permutations are, if we are doing it manually, we have from A, B, C, obviously, in the first place, and A, C, B. Okay. If we try to put B first, we have B, A, C, and then we have B, C, A. If we try to put C, we have C, A, B, and we will have C, B, A. So those are the number of possibilities. But it is easy if we only have 3 variables to choose from. When the number of this gets larger, it is very difficult if we are going to do it manually. So, therefore, there are 6 possibilities. Hence, there are 6 distinct arrangements. Okay. Notice in permutation that it reads ACB, ABC, BAC, BCA as different and distinct arrangement. But in combination, where order doesn't matter, it is simply one combination. Now, so let us try to solve this using our knowledge in factorials and notations. So, in how many ways can we arrange 3 letters A, B, C? So, we can say that this one on the slot method, 3, 2, and 1, that is actually 6 ways or possibilities. Or using factorial notation, we have 3 factorial, which is equal to 6 ways also. So we have another example. In how many ways can 4 different resistors be arranged in series? Since there are objects, the number of ways is 4 factorial or simply equal to 24 ways. That's how simple it is. We have another example here. Let us say this is example 3 and example number 4. In how many ways can a supermarket manager display 5 brands of cereals in 3 spaces on a shelf? Okay, you can do it in 2 ways. The odd method, which is the slot method, and the formula or the factorial notation. Let us try to do this in the slot method. We have 5 brands to choose from, that is n number of things, taken R at a time. We have 3 slots where they can be arranged. In the first slot, we have 5, the second slot we have 4, and the third slot we have 3. Therefore, this is 20 into 3. We will be having, this is 60, right? This is 520 times 3, that's 60. Now, if we want to solve this on another way, so let's try to solve this on another way. So, in how many ways can a supermarket manager display? Let's try the factorial notation. The formula for n number of things taken R at a time is equal to n factorial over n times the quantity n minus R quantity factorial. So if we have 5 numbers of 5 brands, we have 5 factorial over 5 minus 3. 5 minus 3 quantity factorial. And that is equal to 5, 4, 3, 2, 1 over 2 factorial is 2 times 1. This one will cancel out, therefore we have 60 ways or 60 possibilities, same as below. Before we get deeper into problems in permutation, we need to know the theorem on permutation. There are some theorems that will help us solve different types of problems in permutation. For today, we will focus on permutation, and on the next video, I will be focusing on combination. Okay, theorem number 1, arranging n objects. So for theorem number 1, so we are arranging n number of objects, just like what we are doing before, arranging 16 balls on a rack. So that is equal to n factorial. That is the solution. Theorem number 2, so in theorem number 2, we are having number of permutations. The formula is n factorial over the quantity n minus R factorial. And if we have theorem number 3, this is where some complications come along, but it is quite easy if we're trying to dig into it further and to understand it further. In theorem number 3, theorem number 3. We have permutations of different kinds of objects. The number of different permutations of n objects, of which n1 are one of a kind, n2 are second of a kind, and so forth and so on until nk, kth of a kind. For example, we have n objects. And from that n objects, there is n sub 1 which is similar or one kind. Okay? Where's one kind? And there's another similar object that is one of a kind or second kind. Let's say this is second kind. And so forth and so on until there is k or r number of kinds. R kind. So what will be the formula for dealing with this one? The permutation for this one is given by the equation n factorial over n sub 1 factorial multiplied by n sub 2 factorial multiplied by n sub 3 factorial and so forth and so on until it reaches n sub r factorial. So this is the formula. For better clarity, I will be giving some examples involving theorem number 3. For clarity of theorem number 3 in permutation of having different n kind of objects, suppose we have 15 balls on a rack and we want to arrange them. 4 of them is white, which is one of a kind, and the second kind, 5 of them is blue, 6 of them is red. So 4 plus 6 plus 5 will have 15 balls on a rack. So how many possible permutations can we arrange this? So according to the formula that was given to us previously, we have n factorial over n sub 1 factorial multiplied by n sub 2 factorial multiplied by n sub 3 factorial and so forth and so on. This is the general formula for having n number of kinds of permutation having different kinds. So in this example, we have 15 number of things to choose from. We have 15 balls, and then we have to divide that by 4 of them is white, that's 4 factorial, multiplied by 5 of them is blue, and we have to multiply that by 6 of them is red. Remember, and do not confuse yourselves, do not try to multiply 4 times 5 times 6 and you will arrive at a wrong answer. Instead, what I would like you to do or to notice, in this case, we'll have 15 factorials can be written as 15 times 14 times 13 times 12 times 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay, here now. So 4 factorials can be written as 4, 3, 2, and 1. 5 factorial can be written as 5, 4, 3, 2, and 1 multiplied by 4 factorial there. And 6 factorial here can be written as 6, 5 times 4 times 3 times 2 times 1. Notice if we try to cancel out the factors from